Welcome back. So, this is lecture number 51 and we will now continue with a new topic now on differential equations. So, today's lecture will be devoted to the introduction and the formation of differential equations. So, what is the differential equations? So, an equation which involves the derivatives or the differentials of one or more independent variables with respect to one or more independent variables is called differential equation. So, here these are the examples of the differential equation. So, we have these derivative terms involving in these equations and therefore, we call this equation as the differential equation, and this is the ordinary differential equation because these derivatives are ordinary, meaning this we have only one independent variable as x. In this case, y is a dependent variable on x. So, we have the ordinary derivatives here. The second equation, this is also the ordinary differential equation. So, we have these differential terms here dx dy, and this is also having these ordinary derivatives only. So, only one dependent variable, that is y, and one independent variable, that is x. So, for instance, here we have two independent variables, the x and t, and this v depends on two variables here, x and t. So, here we have the notion of the partial derivatives in the equation, and therefore, this is called a partial differential equation or PDE, because here we have the partial derivatives, not the ordinary, but we have the partial derivatives now in the equation. So, there are other classifications here which we call the order. What is the order of the differential equation? And order is nothing but the order of the highest order derivatives involved. So, for example, in this first equation the highest order derivative is 4. So, the order of this equation will be 4. Similarly, we will be talking about the order of these two equations. There is another terminology we will be using here, degree, and degree here in these equations will be the degree of again the highest order derivatives involved. For instance, in this case this is the higher order derivative and the power here is 1, or the degree of this term is 1. So, this is the first degree, but the fourth order differential equation. So, here the order is 4 and the degree is 1. In this equation again the order is 1 because we have the highest order is the first order, like dy dx term will be present here, nothing else, or the first order differentials are present in this case, and the degree is also 1. And in this case here the order is 3. So, because third order derivative terms are there, and the degree is 2 because the highest order derivative appears in degree 2. So, the degree of this differential equation is 2 and the order is 3. The further classifications we will be talking about, like the linear and nonlinear differential equations. So, here a differential equation is called linear if every dependent variable and every derivative occurs in the first degree only. So, if we do not see the product or the power, then we have the linear term, meaning that no product of the dependent variable and or the derivatives occur. So, then we have the linear equation, and if the differential equation is not linear, then we call the nonlinear equation. So, in the nonlinear one, the product of the derivative or the dependent variable with the derivative will exist. So, every linear equation is of first degree, that is clear. Because in linear equation there will be no product or no power. So, it will be first degree, but every first degree equation may not be linear, because for instance, here this is the second order equation and the degree is 1 here, because the degree is defined as this highest the degree of the highest order term, but this equation is non-linear because of this product y and the dy over dx. So, this is a non-linear equation and it is a first degree, but it is a non-linear. So, every linear equation is of first degree, but not every first degree equation will be linear. Now, coming to the solution of the differential equation. So, any relation between the dependent and independent variable without the derivative terms, because in the solution we do not want to see the derivatives will be in the equation, in the differential equation. So, any relation between this dependent and independent variable which satisfies the differential equation is called a solution or the integral of the differential equation. So, for instance, we take this function, this relation between y and x with these two arbitrary constants. What we can check that this is a solution of this differential equation y double prime 2 over y and the y 2 over x and y prime equal to 0. Why this is the solution? Because this relation satisfies this differential equation, which we can easily verify, because if we take the derivative here of this y, we will get minus a over x square, and because we have the second derivative as well in the equation. So, we will go for the second order derivative here. So, y second order derivative will be minus 2a. So, again this minus minus will be plus here. So, 2a over x cube, that is the second order derivative, and if we substitute this here in the equation. So, the second here. So, we have the 2a over this x cube, and then plus this 2 over x, and the first order term here, that is minus a over x square. So, what do we see here? 2a over x cube, and here also 2a over x cube. So, that will cancel out, and we will get the 0, which is the right hand side of the equation. So, what we have observed that this relation, this given relation y is equal to a over x plus b is the solution of this differential equation, because this relation satisfies this differential equation. And now we are going to the direction of the formation of these differential equation. So, before that we need to introduce this family of curves. So, an n parameter family of curves is a set of relations of the form this one. So, here the x y, there is a relation in x y which is defined by this equation f x y C1, C2, Cn. These are the n parameters here equal to 0. So, changing these parameters we will get different curves here. That is what it is, a family of the curves, because different values of these c's we have a different curve. And the examples here, the first the set of these concentric circles, if we take, that means x square plus y square is equal to c, and c is a parameter. So, one parameter family, and the c takes a non-negative real numbers, because here x square plus y square. So, it has to be positive. So, this or non-negative. So, the c has to be non-negative. So, it is taking non-negative real values, and for different values of c, these are the equations of the circle of the same center. So, here it is a family where we have only one parameter, that is c, and if we keep on changing the c, we are getting the circles here with center same and different radius. Again, this set of the circles, if we take here now we are also varying with the center and as well as the radius. So, this is the set of the all circles here. We can choose the C1, C2 and the C3. So, C1, C2 any real number, and the C3 is a positive or non-negative real number. So, in that case this is a family of these 3 parameters C1, C2, C3, while the earlier one was the family of one parameter, because only the radius was varying. In that case, here we have different centers and different radius of these circles, of this family of circle. So, this is the 3 parameter family of circles. And now, what we also observe that the solution of the differential equation, which we have also seen in the previous example, it is a family of curves, nothing else but the family of curves, which we will also observe in next slides. So, how to do this formation of the differential equation for given n parameter family of curves. So, what we will see here, if we have this n parameter family of curves, meaning the solution of a differential equation, then from this given family of curves, how to form the differential equation or the associated differential equation, corresponding differential equation whose solution is this given family of curves. So, from a given family of curves containing n arbitrary constants, we can obtain nth order differential equation whose solution is the given family. So, the order of the differential equation will depend actually how many parameter family we have taken. So, here how to get this actually. So, differentiate the given equation n times and we get n additional equations. There was a given n parameter family equation, we differentiate, keep on differentiating this family. So, we will get n more equations when we differentiate this n times, and out of these n plus 1 total equations, we will eliminate these constant terms or the parameters here, and then we will get equation which will contain only the derivatives terms and the dependent independent variables free from that parameters. So, here by eliminating this from these n plus 1 equations, we will obtain a differential equation of nth order. So, we will see with the help of the examples how this works here, the formation. So, we consider now this example here. So, we will obtain a differential equation which is satisfied by this relation x y is equal to a e power x and plus b e power minus x plus this x square. So, this is a 2 parameter family of curves. So, we have the a and b, they are the arbitrary constants here a and b. So, we have this 2 parameter family of curves. So, out of this 2 parameter family of curves, we are expecting that it will be a corresponding differential equation will be a second order differential equation when we try to eliminate these 2 constants from the equations after taking the derivative of this relation. So, here the given family of curves, we have the x y is equal to a e power x plus b e power minus x plus x square, and if we differentiate this with respect to x, what we get. So, we will get x y derivative plus the y here and the derivative of x 1. So, that is x y prime plus y, that is the derivative of this x y term. So, the product rule applies. Now, the derivative of a e power x, that is a e power x, and then here b e power minus x will be minus b e power minus x, that is here, and the derivative of this x square, that is 2 x. So, we have differentiated this with respect to x only once, and now we have to differentiate this once again, because we do see here 2 arbitrary constants in the equation. So, if we differentiate once again, what we will get out of this x and y double prime, and we will get just y prime. Here also we will get y prime. So, that is 2 y prime, and here a e power x, that will remain as it is. Here the minus minus will become plus. So, we have plus b e power minus x, and then we have this 2 there. So, now we have already differentiated this 2 times, and now we want to eliminate these constants. So, what do we see here, that a e power x and plus this b e power minus x, that is also there in this given relation. So, if we substitute, for example, from here, if we substitute this a e power x plus b e power minus x and put it here in this equation, then these constant terms will be removed, and we will get an equation which contains the derivative terms, dependent variables and independent variables. So, here this using this equation which we call as equation number 1. So, what do we get now? We will get this x y double prime and 2 y prime is equal to. So, this is replaced by x y minus x square. So, here x y minus x square term and this plus 2. So, now we got this differential equation here, which corresponds to this family of curves with 2 parameters, or in other words the solution of this differential equation is nothing but this given family of 2 parameter family of curves. So, that is the how the formation works of this differential equations from a given family of curves, and mainly in this lectures upcoming lectures we will see actually how to find this from this given differential equation how to get this family of curves. So, we have the other concept of the general and the particular solution. So, let this is the nth order differential equation. So, here we have this nth order derivatives and other lower order derivatives, also this dependent variable x and y. So, it is a relation, meaning it is a differential equation, the nth order differential equation. So, what do we call as the general solution? It is a solution containing n independent arbitrary constants. So, in the general solution, also in the previous slide what we have observed, we started with a 2 parameter family of curves, and then corresponding differential equation was second order differential equation, or other way around, whenever we have a second order differential equation and we find the solution of this equation, or rather to say the general solution of this differential equation, it will have 2 arbitrary constants or 2 parameters in the solution. So, here that is exactly the definition of the general solution, the solution containing n independent arbitrary constant. So, any solution of this differential equation of a given differential equation, and if it has n independent arbitrary constants corresponding to this such nth order ordinary differential equation, then we call this solution as general solution. Another one what we are talking about the particular solution. So, giving some values to these coefficients that may depend on some other supplementary conditions may be given along with the differential equation. So, based on the other information, if we can evaluate these coefficients, because this is a general solution is nothing but the family of the curves of this n parameter. So, but having a particular solutions means a particular curve. So, that is possible only when some other supplementary conditions are supplied with the differential equation, and then as a differential equation together with these supplementary conditions we will get particular solutions. So, here the particular solution means the solution giving particular values to one or more of the independent constants. So, usually that is done from the physical model, that some extra conditions are given based on the physics of the problem, and then we can compute actually some or all of the these constants, and the solution here now does not have any independent arbitrary constant. So, which we call as the particular solution. And as we discussed already, that the number of arbitrary constants in a solution of a differential equation depends on the order of the differential equation, and indeed we have seen at least through the examples that a general solution of nth order will contain n arbitrary constants. Okay, so here now let us just go through the examples. So, here we have, for instance, this differential equation dy over dx whole square and minus this 4 times y is equal to 0. It is a general solution. So, we are not finding the techniques or using any techniques to find the solution, that will be discussed in the next lecture. Here we are just providing the definitions. So, for example, this y is equal to x minus c whole square. So, this is a solution, this will satisfy this differential equation. So, if we get here this dy over dx, for instance, it will be 2 times x minus c, and if we substitute now in this differential equation, what will happen, 2 times this x minus c whole square and minus this 4 times this y, that is x minus c whole square. And here also we have 4 x minus c whole square, there also 4 times this x minus c whole square. So, this will cancel out, and what we observe that this solution here, which satisfies this differential equation, and therefore, this is a solution. Also this contains this arbitrary constant, this c. For any value of c, this will satisfy the differential equation which we have observed. So, c is an arbitrary constant, and the order here was 1, the order of this differential equation was 1, and in the solution we have one arbitrary constant. So, therefore, we are calling it as the general solution. Particular solution. So, if we give we assign any value to this c, we can assign directly also, because for any value of c is a solution. So, for instance, if I call that y is equal to x square, so y is equal to x square is also a solution of this differential equation, and by setting just this c to 0. But now this is a particular solution, it is a parabola, it is a fixed parabola, but here that parabola depends on this parameter. It was a family of the parabolas, but now we have a particular curve out of this family. So, we call this as a particular solution, not the general solution. This was the general solution. So, both have the solutions, but one is the general solution, the other one is a particular solution or particular curve out of this family of one parameter curves. Another example which we can look here. So, this is example number 2. So, here this we consider this y prime minus x and y prime whole square is equal to 0. So, if we try to find, I mean that the techniques we will discuss later on. So, this comes to be the general solution of this differential equation, y is equal to c x plus 1 over c. So, here we have this one parameter family, the c is the only parameter in this equation. So, this is a one parameter family of course, and one can easily verify that this also satisfies this differential equation for any value of this c. So, this is a general solution, because the given differential equation was the first order differential equation, and we are getting this solution which is also having one arbitrary constant. So, therefore, we call this as a general solution, but if we give any particular value to this constant, then we are basically selecting one element of this family or one curve out of this family. So, that will be called as the particular solution. So, for instance, in this case, if we take the c is equal to 1. So, here we have taken the c is equal to 1, we have fixed the c is equal to 1, and in that case this y is equal to x plus 1, that will also satisfy the differential equation, and which can again one can easily see. So, the y is this x plus 1, and here y prime will be 1 and minus this x, and then again y prime, that is 1 whole square is equal to 1. So, what do we see the left hand side, this x get cancelled. So, 1 is equal to 1. So, this is naturally satisfying the differential equation, because for any c that satisfies the differential equation. But now, this y is equal to this x plus 1, that is a one curve, the one that is a straight line out of this family of lines. We got this as a particular solution. So, it is no more general solution, this is a particular solution of the given differential equation. There is another terminology used for defining the solution, so called the explicit solution, or we also call as a implicit solution. So, here the explicit solution y is equal to y x, when the solution is given in this form, that y, the dependent variable, is given at the right hand side, everything contains as the independent variable. So, there is no implicit relation of y and x is given, but rather we call this as a explicit relation of y in terms of x. So, we have y is given in terms of x, no other implicit relation. So, this is called the explicit solution. So, if we get out of our differential equation the solution in this form, that y is equal to a function of x, and in case of the implicit solution we get this relation of the x and y, a relation here which satisfies the given differential equation, and therefore, this is called the implicit solution. So, for example, if we take this differential equation, the second order differential equation y double prime plus k square y is equal to 0, and we can observe now by substituting in fact at this point, because we are not going to discuss the solution techniques. This is indeed a solution, because this will satisfy the given differential equation, and therefore, but what else we observe here, that this is the explicit solution, because this y is given in terms of the x. The right hand side here is a function of x. So, this is then an explicit solution is given, y is stated in terms of the x. And now, for the implicit solution, so this is the explicit solution, and there is another example where x plus this 3 y prime is equal to 0 is given, a first order differential equation. And in this case, what we observe, that this x square plus 3 y square is equal to constant. This satisfies this differential equation. So, if it satisfies the differential equation, then this is a solution. So, which we can easily see. So, if we differentiate, for example, this, what relation we are getting, 2 x plus 6 y and dy over dx is equal to 0. So, from here we can compute in fact, or we just divide here by 2. So, we will get here x plus 3 y and y prime is equal to 0. So, naturally it is satisfying this differential equation. So, but what is different here now from the earlier one, here the function of this x y is given, not the as a explicit relation of y in terms of x is given, but it is an implicit relation here given in terms of x and y. So, we call such solution as implicit solution. So, with this we come to the conclusion now. So, we have defined the order and also the degree of the differential equation, and also some classification we have done mainly based on these, whether the equation is linear or it is a nonlinear equation. We have also seen in this lecture that how to this form a differential equation out of the given parameter n parameter family of curves. So, there we have to keep on differentiating this n parameter family of curves n times, and then from the set of n plus 1 different n plus 1 equations, we have to eliminate these parameters, and then we will get a relation of the dependent variables, independent variables and their derivatives, which is the differential equation. So, what will be actually coming now in the future lectures, that how to find the solution of a given differential equation. So, how to find the solution, how to find the family of curves, whether a particular family of curves or the general family of curves of that will be as a solution of the given differential equation. In other words, what we have also discussed here, the general solution of nth order differential equation, which contains n arbitrary constants. So, the general solution is nothing but the n parameter family of curves which satisfies the given differential equation. And these are the references we have used for preparing the lectures, and thank you for your attention.